messing up that incredibly simple problem, 49. We're going to learn about rotational work. This is it. Today is rotational work, and tomorrow is the rotational version of the impulse momentum theorem. So that's it. So today we do rotational work. I want to remind you that in linear land, we have this quantity called work, which is force times distance. Well, you can also have rotational work, where now the work isn't force times distance. I hope you guys know that force is going to be, and I want to tell the audience back home, I'm going really fast because I wasted a bunch of time. So work is equal to torque, and instead of distance, it's going to be the angular displacement. So torque times theta. You guys okay with that? That's our definition for work, but it's rotational work, and so it'll be torque times theta. I also want to introduce another formula we learned in linear land, the fact that net work is equal to the change in the kinetic energy. Well, this equation doesn't go away just because we've now learned about rotational kinetic energy. This equation only gets better. This equation now becomes the net work equals the change in the kinetic energy that's translational plus the change in the kinetic energy that's rotational. That is, the net work on a system is going to be the sum of the changes of the translational and rotational kinetic energies. You guys okay with that? Okay, so let's go ahead and do an example that utilizes this. Here comes example number 1. A 5 Newton force exerted on the edge, a 5 Newton force exerted on the edge of a 2 kilogram, 0.80 meter radius turntable acts for 2 revolutions. And it starts from rest. Let me make sure you understand the scenario. I've got a turntable that's experiencing 5 newtons of force, and that force is going to be perpendicular to the radius of the turntable. That is, the force is tangent to the turntable. I didn't do a very good drawing here. I think it's because I feel like I'm in such a hurry that I end up not doing a good drawing. Okay. If I were to look straight down on the turntable, then it's a lot easier to see. I've got 5 newtons acting at a lever arm of 0.8 meters. Let's go ahead and answer a few questions about this. First, part A, get the rotational work. Get the rotational work. Well, that's easy. I'm just going to use this formula, torque times theta. I hope you see that torque is force times lever arm. And so I've got a 5 Newton force acting at a distance of 0.8 meters from the point of rotation. My torque is going to be 5 newtons times 0.8 meters. That's the torque. And then the theta is easy. My angular displacement is 2 revolutions. Except there's one change I'm gonna have to make. Tell me, whenever I'm dealing with joules or newtons, what units for angles am I gonna have to use?
Radians.
Yeah, radians. You gotta be in radians if you're using, newtons or joules. And so I just wanna remind you that this theta is in radians. So I'm gonna have to multiply this by 2 pi radians in 1 revolution. And then I get my work, which is approximately 50 joules. You guys okay with that? Yay. And so now, here's the next question I want. What is the final rotational kinetic energy of the turntable? I just did 50 joules of work on this turntable. What do you suppose the final rotational kinetic energy is going to be? How many people think 50 joules? Heck yeah, because the net work is equal to the change in kinetic energy. I start with no kinetic energy. I'm not gaining any translational kinetic energy because this turntable is stationary. It's not moving in any particular direction. It's not, translating. So all of that work is being converted into rotational kinetic energy. So yeah, this is going to be 50 joules of rotational kinetic energy. And then finally part C. Part C, I want to find the final angular velocity. Well, to find the final angular velocity, I can just use my definition of rotational kinetic energy. That is, my rotational kinetic energy is equal to 1/2 I omega squared. And then let's plug in. 50 joules equals 1/2 times I. And the moment of inertia of a turntable, which is a solid disk, is going to be 1/2 mr squared. So we got 1/2 mr squared times omega squared. So I got 50 joules equals 1/4 times 2 kilograms, that's what the turntable is, times 0.8 meters squared times omega squared. And so I get a final omega of 12.5. 12.5, if I remember correctly from the last period. 12.5 radians per second. Yeah. Okay. So this is the first thing I need you to be aware of, how to find rotational work and how to use rotational work equals change in kinetic energy. We're now going to do a much harder problem of that. Here comes example number 2. An extremely difficult problem. Let me show you what the problem is. I've got a pulley, and the pulley has 2 masses attached to it. One mass that's 0.5 kilograms, and the other mass that's 0.46 kilograms. 0.5 and 0.46. Under normal circumstances, I would just let the masses go, and the 0.5 would go down, the 0.46 would go up, and I can calculate what the acceleration of those 2 masses are. But that's only good if the pulley is frictionless and massless. But it turns out this pulley has mass. And so because this pulley has mass and thus a moment of inertia, these masses aren't going to fall down or up as quickly as they normally would because they're having to accelerate this big inertia there, this pulley that actually has a moment of inertia. And so let me give you the problem. Oops, I don't want this. The masses move 0.75 meters in 5 seconds. The 0.5 mass going up and the 0.46, the 0.5 mass going down and the 0.46 going up, but they move 0.75 meters in 5 seconds. It turns out the radius of this pulley is 0.05 meters. The pulley starts from rest. I'm asking for a simple thing. Find the moment of inertia of the pulley. There's a name for this type of pulley system. It's called an Atwood machine. Whenever you have one mass going down and another mass going up, it's the Atwood machine. You now have enough information to find the moment of inertia of the pulley. And in fact, I'm in the process of designing a lab for you where I give you some weird shaped hunk of metal and I say, find me the moment of inertia about its center of mass, and you will do something like this in order to find its moment of inertia. It's actually kind of a clever lab that I'm thinking of doing, but I haven't created it yet. Well, it turns out there's 2 ways to answer this question. Can answer in 2 ways. Number 1, you can use torque equals I alpha. That is, all you need to do is find the alpha of the pulley and find the net torque on the pulley. By the way, this is net torque. Find the net torque on the pulley, and you can find the moment of inertia of the pulley. And the other way to do it is to use the net work done on the system equals the change in the kinetic energy of the system. That's 2 ways to do it. And in our remaining, what is this crazy class over, 53? In our remaining 13 minutes together, I'm hoping to show you both ways to do this. And then tomorrow, at the very beginning of the period, I'm going to give you a problem just like this to see if you can do it. The reason I'm teaching this to you is because, in my opinion, it's very likely that our next AP physics test will have something like this on it, because I don't think they've had anything like this on it before, and it's actually a pretty nice little problem. But anyway, here we go. Use net torque equals I alpha. Well, if I'm going to use this formula, I need to get alpha and I need to get the net torque, so let's go ahead and get alpha. Get alpha. And the way I'm going to do that is to get the acceleration first and then use alpha equals acceleration over radius. So I'm going to get the acceleration. I've got x equaling 0.75 meters. This guy's falling 0.75 meters. The time is 5 seconds. The initial velocity is 0, and I'm going to get the acceleration. And so I got x equals 1/2 at squared plus v naught t. I'm just using a kinematic equation. 0.75 equals 1/2 a times 5 squared plus 0. And I get an acceleration of 0.06 meters per second squared. That's the acceleration of those masses, 0.06 meters per second squared. Let me wait a moment while you catch up. Okay, well now that I got the acceleration, I know that alpha equals the tangential acceleration over r. And it turns out if the mass is accelerating down at 0.06 meters per second squared, that means this point on the pulley is accelerating down at 0.06 meters per second squared, and that's a tangential acceleration. So I get to find what alpha is by just using the formula alpha over r, or a over r. So I got 0.06 meters per second squared over 0.05 meters. And so I got alpha equals 1.2 radians per second squared. Believe it or not, I'm halfway there. I found what alpha is. Looks like a 2, of a weird sort of 2. There we go, alpha. Alrighty, hey, part B is I need to find the net torque on the system. Well, looking at the system, I've got two forces happening. I got T1, the torque due to the 0.5 kilogram mass, and I've got T2, the force due to the 0.46 kilogram mass. And I want you to notice that T1 is exerting a counterclockwise torque, and T2 is exerting a clockwise torque. But if I can find T1 and T2, I can get the net torque on the system. Are you guys with me so far? Hoping so. Alrighty, then let's go for it. Here, let's do a free body diagram of the 0.5 kilogram mass. Free body diagram of that mass, I've got T1 up, I've got mg down, and I've got an acceleration downward of 0.06 meters per second squared. And so I get to say that T1 minus mg equals m times negative 0.06. I put negative because the 0.5 is accelerating downward. So I got T1 minus 0.5 times 9.8 equals 0.5 times negative 0.06. And so I get T1 equal to, and just believe me, 4.87 newtons. I'm going to do the same thing for T2. I got T2 mg, and this T2 is accelerating upward at 0.06 meters per second squared. So I know T2 minus mg equals m times 0.06, and that's positive because the 0.46 is accelerating upward. This is of the 0.46 kilogram mass. So I got T2 minus 0.46 times 9.8 equals 0.46 times 0.06. And so I get T2 equaling 4.5356 newtons. And I'm using all the sig figs because I want to get a really precise answer. So now finally I can get the net torque. I hope you see that the net torque is going to be the clockwise torque, T1 times the lever arm, which is R, minus T2 times the lever arm, which is also R. That's the net torque, the clockwise torque subtracted from the counterclockwise torque. And so I got the net torque equaling 4.87 times 0.05 minus 4.5356 times 0.05, and I get a net torque equal to 0.01672 Newton meters. So I have my alpha, I have my net torque. I can now find my moment of inertia of that pulley. This is part C. Net torque equals I alpha. I got 0.01672 equals I times 1.2. And so I get I equaling 0.0139 kilogram meter squared. Let me let you guys catch up. Then I'm going to do it what I think is an easier way. Yes.
In those T's when you're finding the newtons, those are the tension.
I'm sorry?
Is that tension?
Yeah, these T1 and T2 are the tension in the string. So, you know, whatever tension the string is pulling up on the 0.5 kilogram with, that's the same force that the tension is pulling down on the pulley with. So yeah, same tension. Anything else? Alrighty, then let's go ahead and do method 2. Let's use the net work equals the change in kinetic energy. First of all, consider the system. Here's my system. Is there any external force acting on that system? Sure there is. What's an external force? What's pulling those masses down or up?
Gravity.
Yeah, gravity. You okay that gravity, that nothing moves if it's not for gravity. Do you see gravity is the only external force that we're considering? The only force doing work on the system is gravity. Because gravity is pulling this mass down and thus that guy goes up. Also, I hope you see that gravity is doing positive work on that 0.5 kilogram mass. Because gravity, which acts downward, is pulling the 0.5 kilogram mass downward. So gravity does positive work on the 0.5 kilogram mass. What kind of work does gravity do on the 0.46 kilogram mass? Hope you see it's negative, because although gravity is acting down on the 0.46 kilogram mass, the 0.46 kilogram mass is actually going up. Okay, so gravity does positive work on the 0.50 kilogram mass, but negative work on the 0.46 kilogram mass. Okay? Let's go ahead and find what that work is. Work equals force times distance. And so it's going to be 0.5 times 9.8. What distance is gravity pulling it down? 0.75 meters. Minus 0.46 times 9.8 times 0.75 meters. So I hope you see that the work that gravity is doing on the system is going to be 0.294 joules. That's the net work that gravity is doing on the system. I don't have to worry about the work that the tension is doing on the pulley because that's an internal force. I want the work done, by an external force. What work is being done on the system, not what the system is doing it to itself. Alrighty, so now I've got 0.294 joules equals the change in kinetic energy. Because I just found that gravity is doing 0.294 joules of work on the system. Well, the change in the kinetic energy is going to be actually equal to the change in the translational kinetic energy plus the change in the rotational kinetic energy. When I add those two changes together, I get the total change in energy. And because the initial kinetic energy is 0, the initial translational kinetic energy and the initial rotational kinetic energy I can just say it's gonna be the final translational kinetic energy plus the final rotational kinetic energy. Which means I'm gonna have 0.294 equals 1/2 mv squared, the final velocity squared, plus 1/2 I omega squared, and that's the final omega. The last calculation I'm gonna have to make is I need to find the final velocity and the final omega of my system. And we'll do that right now, and if the bell rings, don't leave. My initial velocity is 0, and my average velocity is gonna be the distance they travel divided by how long it takes to travel it. So I hope you see that the average velocity of both masses, whether it's going up or down, the average speed is 0.15 meters per second. Because they both go 0.75 meters in 5 seconds. Well, if my initial velocity is 0 and the average velocity is 0.15, what's the final velocity gonna be? Since they're accelerating at a constant rate? What's that? 0.15? Okay, well that's the average, but that's not the final. It's like in the initial is 0, and the average is 0.15. Yeah, 0.3, twice it, right? Hey, you guys, don't leave yet. 0.3 meters per second. And then, remember how we have this? Omega equals V over R. So, I've got V equals 0.30 over 0.05. That's meters per second, and that's meters. And so this is 6 meters per second. So, I've got my final velocity and my final omega. So let's plug those in. 0.294 equals 1/2. The total mass that's in motion is the 0.5 kilograms plus, and I'm so sorry, I'm going through this so fast. It didn't go like this in the previous classes, I promise. And then this is, what is that, 0.30 meters per second squared plus 1/2 times I times 6 radians per second. And that's not meters per second, that's radians per second. Squared. And of course, if I do all the math, what do you suppose I is going to come out to be? Hope he's the very same. So what I want you to get out of this is that there's 2 ways to do a problem like this. One way using work equals change in kinetic energy, and the other way using torque equals I alpha. And you can do either or both ways. Tomorrow you get another problem just like this. Thanks for your patience. Sorry I had to go so fast. And we'll do it tomorrow, and it will be fun.